critical intensities, understanding why you're doing what you're doing when you're doing it. We're going to do a quick overview of critical power on the bike and critical speed on the run, and why they should be important to your training. So, first slide. Here we have a nice little table. Let me get myself out of the way here real quick. Okay, so on our x-axis, we have our training intensities. Zone R, which is our recovery zone, zone 1, which is our steady state training, zone 2, which is our tempo, zone 3, sub threshold tempo, and then above intensity. Okay. And on the y-axis, we have physiological stability. So we have, here is our critical power line, okay, or critical speed line. Below critical power or critical speed, we have physiological stability. And above it, we have physiological instability. Okay. And across here, across the top, here in this darker pink, we have our type 1 muscle fibers, which encompass all of zone R, and most of zone 1. We have our type 2A. These are our slow twitch, very aerobic muscle fibers. Then we have our type 2 muscle fibers, which are kind of both of these sections, which are broken out into two subsections. Kind of like these are our faster twitch fibers. They're kind of like swing voters in an election, where our type 2A oxidative fibers, type 2AO, they tend towards behaving more like slow twitch fibers, type 1 fibers, and type 2A glycolytic fibers. They they can lean towards behaving like our type 2X muscle fibers. Okay. And so our type 2A muscle fibers will tend to be a little more aerobic in nature, and our type 2A uh, G fibers, our type 2A glycolytic fibers, will tend to be a little more anaerobic or tend towards being a little more anaerobic. Okay. And then our type 2X muscle fibers are our fast twitch muscle fibers. As I said before, this is our critical power or critical speed. This is the differentiator between physiological stability and physiological instability. And then we have our this line right here is a physiological stability relative to the intensity. Okay. And so here in zone R, this recovery zone, this is kind of the equivalent of, if you think of it in terms of like personal finance, this is the equivalent of living well below your means. And as we shift into zone 1, we are living comfortably within our financial means. As we go into zone 2, we are living within our means pretty comfortably, but every now and again, we need to dip into our savings in order to make ends meet. And then as we shift into zone 3, this sub threshold tempo intensity zone, we have this is where we are starting to get in a little more trouble. We are barely living within our means. We are definitely dipping into our savings more and more often to make ends meet. And then once we cross over outside or above our critical power, beyond zone 3 or critical speed, we are definitely living outside of our means. We are spending more than we are taking in on a regular basis. Okay, so why is this stuff important and how is it calculated? So first, why it is important. Where you are physiology, Understanding where your physiology shifts from being stable to unstable. Okay, determining this helps us to determine appropriate training intensity and zones, and it helps us to understand your physiological training needs, which is something that I'll cover in a different presentation later down the road. Right now, we're only talking about the bike and the run. The swim will be covered at a different time in a different kind of way. Uh, so, and how is the how are critical power and critical speed calculated? We field testing allows us to do this outside of a lab setting, which is pretty cool and pretty convenient. And through linear regression applied across three data points, for example, a 3 minute, 6 minute, 12-minute test on the bike, or a 400-meter test, 800-meter, and 3,200-meter, 2-mile test on the run. Um, Really, what we're aiming at here is to test ourselves to see where we land uh, at at short interval durations, longer interval durations, and then somewhere in the middle, medium interval durations. So where our physiology may be a little more anaerobic, where our physiology may be much more aerobic, and then where it is kind of 50-50. Okay. And for running, it's very easy on the bike because we can choose 3 minute, 6 minute, 12-minute to make sure we have a short, medium, and long test. On the run, what I typically recommend is to choose a distance that will take the athlete somewhere between 90 seconds for the short test, plus or minus, so around 2.5 to 3 minutes for the medium test, and somewhere around 10 to 15 minutes for the long test. Okay. And you can choose that, maybe for a particular athlete, it may be a 300-meter uh, uh, short test, a 600-meter medium test, and a mile and a half long test. As long as you know what those interval lengths are, the calculation is pretty simple through the linear regression. All right, so here is a sample data set from a bike test from one of my athletes. So we have the test duration was a 3 minute, a 6 minute, and 12-minute. The average test wattage for each of these test durations was 435 watts for the 3 minute, 375 watts for the 6 minute, and then 336 watts for the 12-minute. Okay, and then over here we use this information to calculate the amount of work in terms of joules that was actually in this ends up being in terms of kilojoules that was done um, for it kilojoules and joules being the same units, just slightly calculated differently. um, so so basically all we're doing is taking our average wattage and multiplying it by our time in seconds. So 435 times 180, 375 times 360, and 336 times 720. And it yields the amount of work completed. We take that and we plot it onto a system. Okay, here's an equation and it creates three data points. Here is our 3 minute test, our 6 minute test, and our 12-minute test. And through linear regression, we're able to determine a line of best fit. Okay, so this is the line that best describes those three data points that the athlete created. On our x-axis, we have test duration, and then on the y-axis, we have the work done in kilojoules. So from that, we can determine this line's, take it back to Algebra 1 class, we can determine this line's slope, okay, its rise over its run, and its y-intercept, okay? And what's nice is that the slope of this line represents the athlete's critical power, okay? So this is the maximal sustainable rate of energy turnover for the athlete. Every second, you can continuously add about 300 joules of work without dipping into your finite bank, which is your anaerobic capacity, your W prime. Kind of think of it as the speed of a treadmill belt that you can keep up with for just about forever. It's really your steady gear. So the slope of this line or the critical power is your steady gear. Okay. And then on our anaerobic capacitance, W prime, this is the y-intercept of this line. And that is 20, so this would be about 25,000 joules, which is five about 25 kilojoules. This is the athlete's finite battery above critical power. Okay. Think of this like a fuel tank. Whenever the athlete goes above 302 watts, they are burning into this tank. They are burning up fuel within that tank. Once that fuel tank is empty, it's empty, and it needs to be refilled through recovery. Okay, recovery being time below the 302 watts. So this is a nice example of how we can, through just 21 minutes of testing, 3 minutes, 6 minutes, 12 minutes, we can determine everything we need to know about the athlete and determine their training intensity. Uh, so calculating your training zones. So we have our training zones, as I outlined earlier, as recovery zone, our steady state zone, our tempo zone, and then our sub-threshold tempo zone. On the bike, it's below 60. The recovery zone is below 65% of critical power and below 75% of critical speed. And the muscle fiber usage is primarily type 1. Zone 1 is our steady state zone. It lives somewhere between 65 and 79% of critical power and 75% and 85% of critical speed. It's primarily type 1 with a little bit of type 2A oxidative. Okay. Zone 2, our tempo zone, is between 79 and 89% of critical power uh, on the bike, it's 85 to 95% of critical speed on the run, and it is all of zone 1, okay, plus an increasing reliance on type 2A oxidative fibers. And then lastly, a subthreshold tempo zone is between 89 and 100% of critical power, 95 to 105% of critical speed, and it's all of zone 2 plus an increasing reliance on type 2A glycolytic muscle fibers. And then back to this slide. So here we have zone R, which is really operating at below 65% of critical power, or below 75% of critical speed. It's almost all primarily type 1 muscle fibers. Then we dip into zone 1, which is 65 to 79% of critical power, okay, or 75 to 85% of critical speed. And that is mostly type 1 muscle fibers with a little bit of type 2A oxidative. And then we go into zone 2 here, where we are 79 to 89% of critical power, or 85 to 95% of critical speed, and that is all of type 1 and all of type 2A oxidative muscle fibers being used. And then we go into zone 3, which is between 89 and 100% of critical power, or uh, 95 to 105% of critical speed. And that is all of the systems, at all of the aerobic systems at full bore. Um, and we use the space between 100 and 105% of critical speed on the run very, very sparingly. Okay. And then the space beat above this, the critical power or critical speed line, where the physiology becomes unstable, as you can see by the increasing inflection point in the curve. This is our W prime. This is our finite battery. So when the athlete goes above this intensity, even for a second, they start dipping into how much of this they have left. Okay, so that is that, and then everything above here is really fueled in a very anaerobic kind of way. So through that relies very heavily on the ATP and phosphocreatine system, as well as anaerobic glycolysis. Glycolysis. If you have any questions, feel free to reach out. You can find us at www.qt2systems.com, email us at services@qt2systems.com, or check us out on Instagram, Facebook, LinkedIn.